Good evening. Welcome to the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. And tonight's topic is an earth science and a surveying topic. What is a topographical map? What is a topographical map? Well, in surveying and in earth science, you have a map, and it reveals the topology of the land. And it has certain symbols that give you an analysis of the land or the landscape of the land. And one part of the topographical map, you're going to see contour lines. Now, pay attention. Contour lines are very important because what contour lines give you are the elevations. Now, here's something you should know as well about contour lines. Contour lines, if they're far apart, they're going to tell you that the land is shallow. And if they're close together, they're going to tell you that the land is steep. Now, when you have steep circles, means you're on top of a mountain range. And also, contour lines show you where all your rivers and your ravines are. Now, in surveying, topographical maps are made by utilizing your survey instrument to locate data. And you can also see topographical maps on software such as ArcGIS. It's a mapping software and something that is very popular out there, and I've used it as well. It is Google Earth. What I'm going to do, I'm going to share my screen, and let's get into it. The changing landscape of topographical mapping. Now, the USGS, which stands for the U.S. Geological Society, produced its first topographical map back in 1879, the same year it was published. Now, today, more than 100 years and millions of map copies later, topographical mapping is still a central activity for the USGS. Now, the topographical map remains an indispensable tool for government, science, industry, and leisure. Now, much has changed since early topographers traveled the unsettled West and carefully plotted the first USGS maps by hand. Now, when we talk about mapping, we look at surveying. Now, in the states, Ohio, and particularly West, they use what we call a public land surveying system known as PLSS. Now, what that does is basically divide your state, and they did it starting in 1785, so land could be sold. And if you look at the Western states, everything is made up of ranges and townships. So what they did is they took a township. The township is 36 or 6 by 6 squares of 36 square miles. Now, within inside that township, you have 640 acres. Now, you have 160 for each quarter. And then you go cut in half, you have 80, you have 40, you have 20. That's how the public land surveying system works. Townships and ranges. Now, when you get to states such as Maryland and New York, they use a system that's predicated by direction. And when I talk about direction, talk about distance and bearing. Like, let's say I have a distance of 300 feet. And what would the bearing be? And I'm going a certain distance, let's say northeast. So put a degree on it. I'm going north 30 degrees, 50 minutes, 41 seconds east. So I'm going northeast about 300 feet. Now, again, that's known as the meets and bounds. Now, again, when you deal with maps, USGS and also the Bureau of Land Management is another place where you can find these USGS maps. And that's where surveying actually got started as well. Now, again, advances in survey techniques, instrumentation and design, and printing techniques, as well as the use of aerial photography and satellite data have dramatically improved mapping coverage, accuracy, and efficiency. Yet, cartography, the art of science and mapping may never before have undergone change more profound than today. Now, a mapping revolution is underway. Why? Because new technologies are altering the production and the use of traditional maps. Even more significantly, the information age has introduced a new cartographic product that is changing the face of mapping, digital data for computerized mapping and analysis. Now, the computer is extending mapping beyond its traditional boundaries. New applications emerge with each technological advance. Now, at their most basic, digital data applications, they make it possible to display maps on a computer, even a home personal computer. And at their most advanced, digital data applications stretch the definition of cartography. Now, what is a topographical map? Well, whether on paper or on a computer screen, a map is the best tool available to catalog and review the arrangement of things on the Earth's surface. Maps of any kind. You have road maps, political maps, land use maps, maps of the world, serve many different purposes. But one of the most widely used of all maps is the topographical map. Why? Because the feature that most distinguishes topographical maps from maps of other types, and I just mentioned it earlier, is the use of contour lines. Just to explain to you what a contour line is. And what they do is they portray the shape and elevation of the land. Now, topographical maps render the three-dimensional ups and downs of the terrain on a two-dimensional surface. So basically, topographical maps usually they portray both natural and man-made features. They show and name the works of nature, including mountains, valleys, plains, rivers, lakes, and of course, vegetation. They also identify the principal works of man, such as roads, boundaries, transmission lines, and major buildings. Now, the wide range of information provided by topographical maps make them extremely useful to professional and recreational map users alike. Topographical maps are used for engineering, energy exploration, natural resource conservation, environment management, public works design, commercial and residential planning, outdoor activities like hiking, camping, and fishing. Now, of course, when we deal with topographical maps, we also deal again with USGS. Now, a long-standing goal of USGS has been to provide complete large-scale topographical map coverage of the United States. The result is a series of more than 54,000 maps that cover in detail the entire area of the 48 contiguous states and, of course, Hawaii. Now, produced at a scale of 1 to 24,000, and some metric maps are produced at a scale of 1 to 25,000. These maps are commonly known as 7.5-minute quadrangle maps because each map covers a four-sided area of 7.5 minutes of latitude, 7.5 minutes of longitude. Now, the United States has been systematically divided into precisely measured quadrangles, and adjacent maps can be combined to form a single large map. Now, the 7.5 quadrangle map series is popular as a base for maps of many different types and scales. And because of its large landmass and sparse population, the primary scale for mapping Alaska is 1 to 63,360, or we say 1 inch represents 1 mile. Now, each Alaska map covers 15 minutes of latitude. Now, the areas covered by these maps vary from 20 to 36 minutes of longitude, and that depends on your location, because there are 2,700 maps in the Alaska 15-minute quadrangle series. Now, in addition to 1 to 24,000 scale maps, complete topographical coverage of the United States is available at scales of 1 to 100,000 and 1 to 250,000. Maps are available at various other scales. Now, the amount of detail shown on a map is proportionate to the scale of the map. The larger the map scale, the more detail shown. Since 1 inch on the map represents 2,000 feet on the Earth, 1 to 24,000 scale maps depict considerable detail. Such large maps of developed areas show features like schools, churches, cemeteries, campgrounds, ski lifts, and even fence lines. Many of these features are generalized or omitted in smaller scale topographical maps. Now, again, they have other USGS, which stands for the United States Geological Society, map products. Now, something you need to know. Topographical maps are not the only cartographic products available from the USGS. Now, the USGS also publishes and distributes a variety of special purpose maps. Now, some of these are topographical and bathymetric maps, photo image maps, satellite image maps, geological maps, land use and land cover maps, and along with hydraulic maps. Now, again, each type of map has a distinct purpose and appearance like topographical maps. All are available to the public for the cost of reproduction and distribution. Remember something, USGS maps are not copyrighted. Now, again, right here is what I'm telling you about some of these mapping scales. You see the contour lines up here. This is a mountain, Mount Rainier. Now, as I mentioned, all of your contour lines that are close like this, that represents the steepness of the slope, and it depicts the mountain. And you can see the numbers, you can see them closely. That's the elevation. And then also their creeks represented, their lakes represented. Now, of course, you have surveyors, and going back, the making of a topographical map, the surveyors, you have aerial photography, and I'm going to post this information right at the bottom of my video. I'm just giving you an overview of topographical maps here. And you can see a lot of surveying technology as I scroll down. But what I want to show you, as I scroll down, see some of the contour lines. Right there, that's 750. That's an elevation. Made at 750 feet above sea level. Of course, you can print maps, you can distribute maps. And here's another one. Man-made features, levee. Got roads. You can even have plats. You have a lot of data. GIS. You know, these maps are also used not just for surveying and engineering. Who else uses GPS and GIS? Well, soil conservation, crime solving. This is how they can locate you. See, if GIS or the GPS breaks down and you know the Latin long, you can use the map. That's why I always say understanding how to read a map is very beneficial. Now, there are a number of individuals who don't know how to read a map because they are heavily dependent on that GPS. Well, when the GPS breaks down, you have to know how to navigate, and that's where a map is your best friend, particularly a topographical map. And it's also used for marketing and emergency resource planning. Now, today we have GPS and GIS, which that involves a lot of surveying operations. And also, this is a map rendered in 3D, and this is what I'm talking about, topography. This is a mountain range. Right here is a river. And if I were to plot this, my contours right here would be very, very steep. In fact, most of my contours would probably range, I would say, count 100 feet, 600, 700, 800. I'm just giving you some examples of what I would put on a map of contours. Now, where do we go from here? With today's technology, it is possible to generate personal maps even on a home computer. And in the near future, traffic jams may be avoided with dashboard mounted computer mapping systems. Beyond that may lie interactive television, where local news or weather reports can be chosen by touching a map on the screen. Digital techniques will continue to influence map making, enabling more paid reproduction of accurate current maps. Computers can also help us manipulate data from traditional maps in increasingly sophisticated ways. Now, that being said, a lot of what you see is data. When you look at all the man-made features and the natural features, well, I know surveyors can go out, let's say they want to locate a tree, they want to locate a road. Well, they take those points from what they collected out in the field and they can put it in a system and utilize a system like GIS, ArcGIS map making. You can also use Google Earth. Again, map making is very important. And as much as people don't understand it, everything we use when it comes to, let's say, you're going out to a shooting range. Well, you need to know your land. You need to understand the unit of mils, which that's target. Where are you going to set up your target? If you're in the woods, you're camping. How are you going to get out of it? You need to understand the land. See, a lot of individuals don't study the land. Like, I watch a show like Amazing Race. The problems that individuals don't do, the big problem, they don't understand how to read a map. When you're in a foreign country, you need to understand that there are certain items like a compass. Now, on a topographical map, you're going to get a true north arrow. When you get north arrow, I'm not going to say true north because it's relative north. The direction where you're going. True north is actually pointing upward to the North Star. But again, they have all kinds of computer software like GIS, Google Earth, that can actually help you with map making. Now I'm going to share my screen and I'm going to get into map making from earth science here. And what I'm going to show you is what kind of features are on the map. And this is very important. What kind of features are on the map? Now, this is from earth science. So without any ado, Let's go ahead.
Cause you're a sky full of stars. I'm gonna give you my heart. Cause you're a sky, full of stars. Cause you light up the park.
Features on a topographic map. This video is going to focus on 4 features that are almost always associated with topographic map questions. Those would be bodies of water, hills and mountains, creeks and rivers, and depressions. Let's begin with bodies of water. Most of the time, topographic maps have some kind of body of water shown. This can be important when trying to determine the elevation of the contour line that's closest to the shoreline. So in this map, Darien Lake occupies this space. And lakes can occupy any elevation, which is unlike oceans, because oceans are really what we base elevation on. When we say something's at sea level or above sea level, what you're saying is it's above the height of the ocean. If you were to be asked what is the elevation of the coastline along Darien Lake, you would need to find that out using the information here. Now, it's not shown, but the contour interval is 10 feet. And if I'm using the index contour that's already drawn closest to the shoreline, I would come up with a value of 240 feet. And this is important because that means anywhere along the coast. So if you think about how that coast stretches, anywhere along there, we're starting at 240 feet. And that's a very important number to have as I look across the map.
And the reason why he's talking about the interval of 10 feet and along the coastline is 240 feet, because again, at sea level, Pete, what was just said, we're dealing with anything at ocean level. Now, if you look at the city of New Orleans, they're 21 feet below sea level. This is why they have levees, which means if my coastline here is 240 feet, now this is above sea level. Well, what would New Orleans be? Well, at sea level would be 0. And then minus 21 feet would be where New Orleans is, because you're 21 feet below sea level. Now, anything that's above 240 feet, you're going to get what we call, and we're dealing with depressions here. 250, and just like I told you, this contour line, like Amherst Hill, it's right around, I'm going to say 310 feet above sea level. And these are the contour lines. And this 300 right here, this is your elevation. And as you see how close the contours are, the closer they are together, that's steep. The farther apart, that means it's less steep. Let's continue.
When a map displays an ocean, well, then we can start to think about beginning at 0 sea level. And that's unlike the Darien Lake situation. And notice how there's no contour interval given here. We'd have to figure it out. And because we know that oceans begin at 0 elevation, we could do that using the index contours on this map. So we know that it's 100, let's say, feet up here on the island. And if I'm starting in here, which is 0 feet or 0 elevation, and I have to cross 1, 2, 3, 4, 5 lines to get to 100, I know that it's going up by 20 feet. If I start at 0, 20, 40, 60, 80, 100. So knowing that piece of information, that oceans the shoreline starts at 0 is really important when you're not given a contour interval, and that might happen on different maps. Let's look at another example here of a pond. Ponds are a lot like lakes, same situation. They can be at any elevation. So we want to know what is the shoreline in this pond. We have a contour interval of 10 meters. We have an index contour of 50. So that means if I'm starting here at the shoreline, it's got to be equal to 30 meters. 30, 40, 50. So I'm starting at 30. Now let's take a look at another feature, very common to topographic maps, and that's hills and mountains. Now, topographic maps are drawn to represent three-dimensional structures in a two-dimensional space. This hill or mountain, whichever one you want to call it, would look like this from a side profile. So if you saw it in real life and you were standing in front of it, this is what it would look like. If I want to convert it to a topographic map, this would be its equivalent. Note the closeness of the lines on the left-hand side. Okay, if you look here, the lines are much closer together on this side, the left-hand side, to correlate with this part of the mountain, which shows a very steep incline, and a much more gradual slope on this side to show a much more flat terrain in this structure. To give you another example, this again is a two-dimensional shape, but when we project it into a side profile, this is the type of structure it would come to. And if you look at the series of circles within each other, you can see that the two reference points, the smallest circle, which is on the inside, refers to the peak of the mountaintop. So always kind of correlate that as the circles get smaller and smaller and smaller and smaller, the last circle is going to represent the topmost point of whatever structure you're dealing with. Now, depressions can also be shown because not only does the ground always increase in elevation, sometimes the terrain goes the opposite way and gets deeper. And to show depressions, topographic maps use Hochscher lines. Okay, now Hochscher lines have little dashes associated with them. And those will tell you that the ground is actually going down instead of up. And there's really two things to always consider when you look for these features. Hochscher lines point towards the center of the depression. So these arrows I added in, they're not typical on a topographic map, but notice all those Hochscher lines are pointed towards the center, towards the letter E. That's the direction that depression goes in. And if you were not given information associated with the values, this one happens to give you the index contour. If you were asked what is the value of the depression lines in this feature, the first Hochscher line is always going to be equal to the last contour line that you crossed. So in this case, the value is 50 feet because the last line that was crossed was this 50 meter line here. So that was the last ISO line crossed, so this would be 50. So it repeats itself. And then the next line inside would be the contour interval, but going down. All right, so let's look at a few examples to kind of practice this because it's definitely a different point of view. All right, so here we are back at Darry Lynn Lake, and let's zoom in on the depression contour in this map. So you're given an index contour here that shows a 250 foot index. So I want to know, what is this value? What's this equal to? Well, if I know the contour interval, which I do, it's equal to 10 feet. I can easily say, okay, this is going to be equal to 260, but let's just verify it by using the information that we have here. This index contour here is 300. So if it's 10 feet, this is going to be 290, 280, 270. So 270, right? This next one's going to be 260. So if this is the last contour line that I crossed, so to speak, this one would have to be the same value. So that would give me a contour line or depression line value of 260. All right, let's try another example. This one's now a lot harder because there's no reference given. So the index contour we're given here is 200, and the contour interval, if I look over here, this is 180, this line is 200, so I know that there's a contour interval of 20 feet. So if this line is 200, this one's going to also be 200, and this would be 180. So a really challenging question to ask about Romano Swamp is, what is the lowest possible elevation for Romano Swamp? And it's working in the opposite way than you're used to. So if I know that this outer line is 200 and this depression contour is equal to 180, I can't say that Romano Swamp is at 180 feet because it's within that series of circles. So it's got to be a number lower than 180. But it also can't be a number lower than 160, because if it was, there would be another set of depression contour lines inside of here, but there's not. The lowest I can go for this value is anything between 179, which is less than 180, all the way down to 161 feet. Because if I were to go to 160, I'd have to have a new depression contour line drawn. So if that was a question you were to be asked, it would have to be an answer within that range of 100.
Now, what you would do for that type of problem, you would use, some people would average, but if you really want to find out what the actual elevation is at, you're going to have to use some interpolation. So how would you interpolate this? Well, you're going to have an X value. You're going to have to take your largest number, find the X, and then your lowest number. And when you go in interpolation, it could be 178.5. But again, now he's going to tell you something different, but I have done problems like this in the past. Interpolation is the most accurate. But let's see what he's going to do. Fair use. Let's continue.
179 to 161. All right, let's move forward. All right, so for our final feature, we're looking at creeks and rivers, which also includes streams. They can be treated all the same. Most topographic maps will feature at least one or two rivers, creeks, or streams. And this map happens to show the Newburgh River and two tributaries, the Brigitte and Zemp Creek, which kind of fill into the Newburgh River. And typically what you'll be asked to identify is the direction in which they're flowing in. Is that rivers will always flow from high elevations to lower elevation. And let's go back to that same river now, which we were looking at the Newburgh River and saying it flows this direction. And if I was going to give it a direction, I could say south, but a better answer would be southwest. But this is logical. I have here drawn in the different elevations for this contour map. It's 160, 140, 120, 100 feet, and then so on and so forth. Rivers are going to flow downhill. They're always going to seek out, water will seek out the lowest point and travel in that direction because of gravity. So I'm flowing from a higher elevation to a lower elevation. So it just seems logical that this thought process would work. Think about any stream or river that you've ever encountered. It always seems like the rocks or whatever makes it up are like steps, and it's flowing down the steps because of gravity. There's a misconception, though, a silly misconception that throws people off regarding this, and I just want to point it out here, is that all rivers have to flow south, because somehow people have associated going south with going downward in real life. Like if you were to go down on an elevator, you're really going south, which is not true at all.
No, that's not true. In fact, the Nile River actually flows north. Fair use.
Going down, different direction than going south. And this is a good example here on this map. The Cinder River is actually flowing northwest, to be totally accurate, which is not against gravity. It's just the direction that the river's flowing to get back to the Atlantic Ocean. So don't make that same connection that rivers have to flow south. That's totally not true. To always figure out the direction a river is flowing, and those are called V-shaped contour lines. If you look for them in a topographic map, they're always pointing upstream. And if the V-shaped lines point upstream, a river is going to flow opposite. That sounds like a lot of information, but when I show it to you here, it's going to make a lot more sense. So in my map, if I look carefully at the Newburgh River, I can see that there are these V's across it. And those are how the contour lines are drawn and bent. I can go all the way up to the top. Those V's are all pointing this way. So the river is flowing in the opposite direction. So whatever direction the V's are pointing in, the river will flow the opposite way. So for the Brigitte River, apply the same thinking. Look at those V's. River's flowing opposite to those. Let's look at this stream here. Here's my V-shaped lines. All right. So they all seem to be pointing this way, but the river is actually flowing, or the stream, I should say, is flowing that way. So one more example. All right, the Stone River. Stone River is shown here. Okay. Is it flowing into Pebble Lake, or is it flowing out of Pebble Lake? So here's my V-shaped contour lines. Right? My V-shaped contour lines. They're pointing upstream. The river's going to flow opposite. So in this case, the water's flowing out of Pebble Lake and down, well, I should say northeast across the map. So we'll practice more in class, but that's all for now. Thanks for watching.
And again, when you deal with a topographical map, you just show the contour lines. And when we deal with topographical maps, okay, again, we must understand that we're dealing with man-made features, we're dealing with natural features, we're dealing with a 3D topology of land on a two-dimensional type scale. And what you just saw were depressions and contour lines. And very important that you understand that. And the one that does get a lot of individuals in trouble is the V. Now, again, as I put it out here to you, and let me draw it myself here, and I can present it to you. If I have a river, I'm going to draw it right here so you'll know it. And I have 200, 150, and I have a V right here. All right, I have a V right here. Okay, now, where that V is, everything is pointing upward. See, everything is pointing upward. Now, what does that mean? That means my river is flowing downward. It's always the opposite direction of the V. And it is true. And I mentioned the Nile River. Rivers always flow from highest elevation to lowest elevation. But it doesn't mean that rivers all flow south. So again, when it comes to finding a number of contours that aren't there, you can interpolate. And there are different ways of doing it. Now, one of the ways to set up is if I have a proportion, 100 over X equals 50 over 20. Set up a proportion. And what I would do, I would say 50x equals 200,000. And then I would divide both sides by 50, and I'd come up with a number. I'd come up with 4,000, something like that. Always set up a proportion. That's another way you can interpolate. But again, features that are important are your mountain ranges, rivers, creeks, which are all water beds. You're gonna have roads, you're gonna have bridges, everything that constitutes a map. And something important you're gonna have on that topographical map is your north arrow. And again, just gave you an overview of what is a topographical map and what they're used for. And that concludes this topic on what is a topographical map. If you like what I just presented, please comment, share, and subscribe. And if you are looking for some political and some social content, you can check out my other channel, the 411 Talk Zone radio show. And generally every Wednesday, I put up a topic on the 411 Talk Zone radio show channel. Now, if you cannot find the 411 Talk Zone radio show or the QCIS channel on YouTube, you can check both of those channels out on Twitter. Now, for the QCIS channel, I'll take it one step further. You can also find that channel on my LinkedIn page. Once again, thank you for listening to the content of What is a Topographical Map? Right here on the QCIS channel. On this channel, get a daily dose of science, technology, engineering, and math. Until next time, my name is Leon Jones. I want you to have a wonderful and blessed evening. And good night. And once again, my name is Leon Jones. And again, have a pleasant night. And I will be bringing you more of this content in the future.